All right, what is up, everybody? Welcome to day 3 of the ratio and proportions review. We got the warm-up, a little bit of notes, and then the practice at the end. So, number 1 from the warm-up, which of the probability has a probability of 1 in 6? We have 4 different choices. Number A, or letter choice A, we have heads and tails. We're looking for tails. Well, there's 1 tails out of 2 sides, not 1 out of 6. Letter choice B, rolling an even number. Well, they're talking about the even numbers of a dice. 2, 4, 6. 3 numbers out of a total of 6. 3 out of 6 is really 1/2. So A and B, both eliminated. C and D. Well, C still talking about rolling a dice. There is 1 5 out of 6 choices, so that does indeed have a 1 in 6 chance. Answer choice D. Well, if there's 1 heads, there's 1 tails. There's still 2 sides of the coin, so A and D are equally likely. Letter number 2. Mr. Tucker earns $250 a week, so we know for him showing up to work, he automatically gets $250. What other money does he make in addition to that? He earns 2% commission on everything he sells. Well, he sold $2,800 worth of material. So, first step, 2,800 times 2% because he gets 2% of the sales, and he sold 2,800 worth of appliances means he made $56 in commission. But not only did he make the $56 in commission, he also earned his salary of $250. So $250 plus the commission means he made a total of $306, letter choice C. Number 3, a scale factor problem. We have our ticket right here giving us our scale. 1 inch represented by 3 feet. We want to figure out if a rectangular garden was 4.5 inches long, what would the actual length be? So again, we kind of set up our ticket. We know that our units are inches over feet because of our scale. We know our ratio is 1 inch is 3 feet, again, because of our scale. And then again, we have that 4.5 inches. So I know I have inches on my top. We don't know how many feet that would be in the bottom. So 4.5 over x. This problem, fairly simple, because all you had to do is cross multiply. 1 times x. X is already by itself. 3 times 4.5 is 13.5. Number 4, easy 2-step equation. First step, we're trying to get 2 times x by itself. Well, I have this minus 6 on the same side as my variable side. So the first step, add 6 to cancel the negative 6 out. 6 plus 6 is 12. 2 times x is the same as 12. Well, I said times 2, so I divided by 2. And 12 divided by 2 is positive 6. All right, moving on. First up today, we're going to do our daily dose of algebra. So, again, being able to take these problems, break them apart, make the problem easy with fractions and the use of a calculator. So, remember, first off, we're going to read the math to make the operations a little easier to deal with. 6 times 4 times x, all being divided by 2. 6 minus 4 times x, all being divided by 2. So remember, everything is over 2 here. This entire top expression is all being divided by 2. So the first step, I'm going to break it apart. 6 divided by 2, I'm keeping the minus sign because there's only one symbol in this problem. So drop the minus down. 4 over 2, 4 divided by 2 times x is the same as 4. Well, first off, trying to isolate x. Really important that you're seeing that this coefficient is a negative 4 over 2 times x. So the first thing I need to do is get rid of the positive 6 divided by 2. Well, to get rid of a positive 6 over 2, I subtract 6 over 2. One side cancels. 4 minus 6 over 2 is positive 1. So again, dropping down my negative 4/2 times x. Well, I said times, so I divided each side by negative 4 over 2. And 1 divided by negative 4 over 2 is negative 0.5 or negative 1/2. So again, keeping your work nice, neat, organized all the way through the problem, isolating your variable, getting a good answer. All right, today we're going to be dealing with a bunch of different scale factor problems, okay? Some of them we're very familiar with. Some of them we got to use our brain and kind of think about what knowledge do we have and how can we apply that to some problems to solve. So, real quick little air analysis. The Empire State Building is 1,250 feet tall. That's an actual length or height of the building. Maria wants to make a model that has a scale of 1/2 feet is the same as 50 feet. How tall would her model be? Well, first off, let's look at the work that we already have for this problem. This person, they use the scale 1/2 over 50. Okay, that's actually pretty good because that is the scale. 1/2 feet equals 50 feet. When they went to plug this in, they put 1,250 over x. They cross-multiplied. Everything is great there. 1/2 times x is 1/2 x. 50 times 1,250 is 620 or 62,500. They divided by 1/2, and they do have a correct answer there. But here's the issue. That doesn't make sense that the model would be much bigger than the actual building. Something went wrong, because I know that a model should be smaller, a small representation of something that's very large. Okay, so let's take a look at this. Well, the one thing that I notice is missing is a ticket. There's no ticket here. So let's kind of figure out if that's where our student made a mistake. In our scale, we're comparing feet to feet. Well, feet and feet is not a good way because everything could be placed anywhere. So we got to think, what else is being compared here? They have the actual building, and then they want to make a model. Well, if I think about the given ratio, the model must be the smaller number, and the actual building would be the bigger number. So let's see if everything works out. 1/2 for the model, yes. 50 actual, yes. 1,250 for the model. Well, that's the actual height. So where this student really made this mistake was right there. They put the pieces on the solving side in the wrong place. So down below, I kind of worked out this problem. Again, using the ticket, model over actual. 1/2 for the model, yes. 50 feet, actually the feet, yes. Do we know the actual? Yes. Do we know the model? No, that's my variable. Again, cross multiply, 50 times x is 50x, 1/2 times 1,250 is 625. We divide each side by 50. One side cancels out. 625 divided by 50 is 12.5 feet or 12.5 feet. The model is now 12.5 feet, and the actual building is 1,250. That makes much more sense. So the actual thing is bigger, and the model is a smaller representation of that actual building. All right, we're going to use a lot of that same knowledge to go through these problems. So, first one, model using pictures. Well, it says that a 4 by 6 inch frame was proportionally enlarged as shown. So enlarged just means it got bigger. What is the length of the unmeasured side, and using this, and what is the scale that was used to enlarge the picture? So there's two things going on here. We want to know what is the length and how did it get enlarged? What was the change from the small picture to the big picture? Well, again, we're comparing inches to inches in this problem. So inches over inches can't be used. So let's again think about, well, what did they give us? They gave us a length and a width. So I could use that because both pictures have a length and a width. So that was my ticket for this problem, comparing length to width. Well, I know that the length of the smaller picture was 6 and its width is 4. I know that the width of the bigger picture is 6, but I don't know its length. So again, cross multiply. 4 times x, 4x. 6 times 6, 36. We have 4 times x, so I divided each side by 4. 36 divided by 4, x equals 9. All right, well, that's great, but here's the issue. That only eliminates two answers, D and A, because they say x should be worth 6, not 9. So, again, I've kind of already gotten a 50% chance better at getting this problem correctly just by solving and getting that 9. But I got to think, how did they enlarge it? Well, 6 times something gives me 9. I know that because it was enlarged by a scale of something. So if I think, answer choice B, 6 times 2, well, 6 times 2 is 12, not 9. So B can't be right. Yes, the length is 9, but it was not enlarged by a scale of 2. 1.5 times 6 is 9, and this has a x equals 9 and the correct scale, so we would say that answer choice C would be the best answer there. Again, setting up a proportion ratio to figure out what would the new length be, and then thinking about, well, how did it get changed? What was the scale used to get from the original picture to the new picture? Second example I have here for you. So again, model using same units. So again, when I read this problem, a Navy submarine weighs 5,321 pounds. During the construction, they used a model with a scale of 1/2 pounds equals 50 pounds. How heavy was the model of the submarine? Well, again, I can't use pounds and pounds because, again, these do have to get put in a certain order. They can't just be randomly put in. They gave me three numbers all using the same units. But I know that this is changing. Well, what's changing? We have a model submarine and we have the actual submarine. So the first thing, again, I found a different way to kind of compare this model to the actual. I know the model has 1/2 pounds represents 50 pounds. And if I read carefully, I just got to think, what did they give me? Did they give me the model or the actual weight? The actual weight is 5,321 pounds, and we don't know what the model would be. But I know if I set up my proportion correctly and I cross multiply and isolate my variable, I can get an answer. So 50 times x, 50x. We cross multiply 1/2 times 5,321. We get 2,660.5. I divided it by 50, and I found out that the model would weigh 53.21 pounds. And again, that kind of makes sense. If you think about proportionally, I have a smaller number over a bigger number. I have a smaller number over a bigger number. It at least checks out as far as looking correct. If you had gotten an answer that was much larger than the actual thing, then you'd have to think to yourself, well, that can't be right because a model is a smaller representation of a real life, larger figure. And next one, last one on model, this kind of puts everything a little bit together. A new playground has a length that measures 20.5 meters and a width that measures 12 meters. If a scale drawing has a width that measures 6 inches, what is its length in the drawing? Well, first thing I did, they gave me a rectangular garden or playground, so that's what I went ahead and drew. 20.5 is its width, 12 was its length. And then I drew another rectangle because it appears that we're using a scale drawing. So again, they're taking something that's really big and shrinking it down. They told me what the width would be, but we don't know the length. So again, what are we comparing in this problem? We are comparing its length to its width. Again, if I set this up as inches over meters, it can be done, but it gets a little tricky trying to think about, well, what goes with what? The easiest way is, again, we're comparing a length to a width. Comparing a length to a width. Well, on the actual playground, we know that its length is 12 meters and its width is 20.5. On the smaller drawing, we know that its length is 6 inches, but we don't know what its width would be. Again, I cross multiply once I have it set up. I'm going to find that 12 times x is 12x, 20.5 times 6 is 123, divided by 12, and I find out that the actual width was 10.25 inches. So again, sometimes you just got to be careful. There's what's the best way I can compare these two different things. Sometimes if the units are different or the same and they're not different, you got to find a better way, whether it's comparing a model to an actual, a length to a width. There's other ways to do these problems. You just got to kind of think them through. So at this point, I would go ahead and pause the video and take a try at these last couple before you get your independent practice. When you're done, unpause the video and I'll go over them. So first one, a photographer has taken a skyline picture below. The photograph was taken in a mural and was shrunk down. So we had a big picture trying to get shrunk down to a smaller picture. And we want to see, again, what is the missing length and what was the scale used to enlarge or shrink this picture? Well, first off, again, everything's in feet, so that is not going to help me compare these two pictures. I know that they gave me a length and a width. They gave me a length and a width. So again, first off, compare your units. How can I compare them with their length and width? I know that the smaller drawing has a length of 2.5 or 3.2 feet, and we don't know what the width is, so I gave it the variable n. On the actual picture that we had, we know that its length was 16 and that its width was 84.5 feet. Once I have it set up, cross multiply, divide by your coefficient, and you would have found that the missing side was 16.9. In this one, I only see the length being measured, the width being measured by 16.9 feet. So answer choice B is the only answer. But again, if I kind of think about it, it's saying that 16.9 was enlarged by a scale of 5, and 16.9 times 5 does indeed give me 84.5. So this problem checks out on every level. Second one. A developer made a model of a new apartment building. The model is construction so that the scale of 1/4 foot is equal to 5 feet. If the apartment building is going to actually be 840 feet tall, how tall is the model? Well, again, Everything is in feet, so that is not going to help me compare this problem. What are they comparing? They're comparing an actual building to its model. So again, using my ticket, model over actual. In this problem, they gave me my scale, 1/4 is the same as 5, so 1/4 over 5. We don't know what the model's height would be right here. How tall is the model? We don't know, but they told us that the actual building was 840 feet tall. Again, you cross multiply, you divide by your coefficient, you isolate x, and we would find out that the model was 42 feet tall. So again, hopefully you've got all your notes in there. From there, you have your bit.ly, raise your hand when you're finished, and we'll go from there.